Let us discuss the notion of linear space. Essentially, linear space is a set of elements which can be added to each other and multiplied by numbers as if they were the standard vectors known from the high school. For example, let us consider the set of polynomials p2 with degree 2 or less. Any such polynomial p can be written as p of t equals to a2t squared plus a1t plus a0 for all t. The numbers a2, a1 and a0 are called the coefficients of the polynomial p. Let us turn p2 into a linear space. Given another polynomial q in p2, what does it mean to find the sum of p and q? Let us define the sum p plus q to be a function of t given by p of t plus q of t for all t. Similarly, given a number alpha, what does it mean to multiply p by alpha? We define alpha times p to be a function of t given by alpha times p of t for all t. These functions are not arbitrary functions of t, but as it is easy to see, they are polynomials with degree 2 or less, so we can write that p plus q belongs to p2 and alpha times p belongs to p2 as well. In particular, if we take alpha to be 0, then let us denote by z the polynomial 0 times p. Using this formula, we see that z of t equals to 0 for all t. Such polynomial is called zero polynomial, and it plays the role of the zero vector. For example, p plus z is p for any p in p2. The last but not the least is that our operations of sum and multiplication by a number satisfy all the natural rules which hold for the standard vectors. For example, p plus q is the same as q plus p, and alpha times p plus q is equal to alpha times p plus alpha times q. Thanks to the rules like this, polynomials are similar to vectors with respect to operations of sum and multiplication by a number, and this makes p2 a linear space. Polynomials and standard vectors are very different objects. Polynomials are functions, and standard vectors are directed segments. For example, two standard vectors are equal if and only if they have the same direction and the same length, while two polynomials, let's say p and q, are equal if and only if p of t equals to q of t for all t. In particular, the equality p equals 0 polynomial holds if and only if p of t equals to 0 for all t. By the way, since any polynomial has only finitely many roots, this equality holds for all t if and only if all the coefficients of p are zeros, so a2 equals a1 equals a0 equals 0. The similar statement holds for the polynomials of higher degree as well. So you see that polynomials and standard vectors are quite different. On the other hand, there are some similarities. For example, for any number alpha, the identity alpha times p plus q equals alpha times p plus alpha times q holds no matter if p and q are polynomials or vectors. The bottom line is that polynomials and the standard vectors have different nature, but they are similar with respect to the operations of sum and multiplication by a number. This analogy between polynomials and vectors allows us to define for the polynomials the properties which are defined for vectors. For example, let us give a definition of parallel polynomials. We say that polynomials p and q are parallel if q is 0 or there exists a number alpha such that p equals alpha times q. For example, polynomials t plus 1 and 2t plus 2 are parallel. Indeed, I can write this polynomial as 2 times t plus 1, and so if this is p and this is q, then this definition holds if I take alpha equal to 1/2. Let me give you another example. Polynomials t squared and t are not parallel. Let us prove this. Suppose that they are. Since both of them are non-zero polynomials, we can write that there exists alpha such that t squared equals to alpha times t. This equality should hold for all t, and this is very important. Let me rearrange it in the form t squared minus alpha t equals 0. So this identity holds for all t if and only if 1 is 0 and minus alpha is 0. This contradiction proves that such number alpha cannot exist, and therefore this definition does not hold, hence these two polynomials are not parallel.